ask your friends to join because I have another class after this session, and this particular session is being taken at this odd hour as I'm involved in faculty development program. So sorry for this inconvenience. Last class I discussed about cyclic group. In today's class, I'll again discuss about some more aspects on cyclic groups. But before that, I think one or two problems related to subgroup will be important, and they should be discussed before I proceed further. We have not done any problem related to subgroups, so let us solve a few problems on that, and then I'm going to discuss on cyclic groups, because cyclic group chapter is very important, and the results which I'm going to show you, the examples that I'm going to show you right now related to subgroups will somewhat applicable to cyclic group also. So that's why I'm actually concerned about these particular problems. So my first problem, and these are problems, not theorems. Remember, my first problem of today's class is actually from subgroups, because what happens is that why am I concerned about subgroup is, if I consider this set capital G and if I define an operation on that, that structure that is obtained, which is called group, we often like to discuss, we often do not like to discuss about the entire group. What we want to do is that we want to select a part of that, which is a subset of that set capital G, and we just want to see whether this set capital H is a group with respect to the same operation as defined on capital G or not. And if we can find that yes, this H is also a group, then we call this H to be a subgroup of G. What are the conditions for a particular set to be a subgroup? The condition is that, first of all, this set has to be a subset of the original set. This is the condition number one. Condition number two is that this set capital H should be non-empty. And condition number three is that if we take two elements from the set capital H, then A, B inverse must also belong to capital H. If these three conditions are satisfied, then we say that a particular set is a subgroup of the given group. So my first problem is that if capital G is a commutative group, I think you do not have any problem with this abbreviation. This abbreviation is for the word commutative. I have written in short. Sometimes it is also known as abelian group, you know. So if G is the commutative group, then we are supposed to prove that the set capital H, which is defined as this set is a set containing all the elements of G, those elements of the group G for which A square equal to E. And we are supposed to prove that it is a subgroup. It is a subgroup of capital G. Now what we actually want to show over here, it is about showing these three properties. H, these properties that I have written over here. Now we shall try to check whether for the given set these properties are satisfied. We are going to check it one after another. Now, first of all, let us try to verify the property number one. We see that each of the elements of the set capital H, those elements are special type of elements, but the elements have been chosen from the group capital G. So we see that all the elements of H, which we actually denote by A, are taken from taken from the group itself having some special property. And therefore, it is quite obvious that this set capital H is a subset of capital G. So first property is satisfied. Now we are going to write number one. This property number one has been satisfied. Now next we are going to check whether this set is non-empty or not. So for this, I'm writing it in this manner. Since capital G is a group, so it has an identity element. It has an identity element that we denote by small e, say. Okay, and it is quite obvious that if we write e square, if we try to calculate e square, it is nothing but e into e, which is equal to e. So e has the special property as depicted in the set capital H. All the elements of set H will be such that when we take its square or when we multiply the element by itself, we get the identity, which is true for E. And this implies E belonging to capital H. Since the identity element of the group G is in the set H, so therefore H is obviously not equal to pi. So here, if you if you look at the picture, you see that if capital G is the group and identity element is E, then this identity element is residing somewhere inside capital H for this scenario. So the second property is also satisfied. So we write equation number 2, or we are naming it as 2. Next, we are going to use the definition. The third definition is important. It is saying that if we choose two elements A and B from H, then AB inverse must belong to H. Okay, so let us try to check it. Let us consider two elements from the set capital H. And if we choose two elements from the set capital H, immediately they imply that A belonging to capital G and S squared equal to E. This is one scenario. Another scenario is that B belonging to capital G and B squared equal to E by the property of capital H. Okay. And this implies that A belonging to capital G, and we can write it as A is equal to E, and B belonging to capital G and B is equal to E. Why am I writing it in this manner? We have a special purpose for doing this. What is that special purpose? Remember that capital G, since is a group, so every element A of G has its inverse, which we can denote by A inverse in capital G. Okay. And therefore, we can multiply both the sides of the equation by A inverse. So we can multiply this by this in this manner, and we can multiply that part in this manner. So we are writing it in this way. Okay, and since the elements of group G are associative, I mean capital G is associative with respect to the operation, so we can rearrange the terms in the following manner. So we can write it in this manner: A inverse belonging to G, A inverse is equal to E into A inverse. So this is written as A inverse, because any element multiplied by E gives the same element. Similar thing has happened here also. So we can write it as B into B inverse, which is equal to B inverse. And Again, you know that A inverse is equal to E for all A belonging to G. So therefore, we can write it as A inverse belonging to G and A is equal to A inverse, which is from this particular side, and from that particular side, we are going to get B inverse belonging to G and B is equal to B inverse. So up to this, we have done. Okay, so if you want to take the screenshot of this page, you can do. I'm going to move on to the next page because I think writing, understanding is important, but writing all the lines now will just kill your time. So just quickly take a screenshot and save it somewhere. So I'm going to the next page. Before I do so, let us name this particular expression that I have obtained. Let us name it by star, because maybe we shall be requiring star in the next phase of the problem. Okay, but what I will ask you to do is that just try to follow the logic. Here the logic is very important. Try to follow the logic by which I am approaching to prove the given result. This logic is very important. I am somewhere writing comma, somewhere I'm writing and, somewhere I'm putting brackets, somewhere I'm writing implies. So all these things are actually being taken care of seriously. So if I do not write comma here, if I write and or if I write or, the meaning will change. So you have to decide what you should write to prove in such kind of topics of pure mathematics. Okay, so be careful about that. Now, according to the definition, according to the property of the subgroup, this has to be true. So if we select two elements A and B from H, we must show that AB inverse belonging to H. Now, carefully observe that if we want to, it is a rough work I'm doing over here. I'm not writing anything, it is a rough work. If I choose two elements, if I want to show that AB inverse belonging to H, then we actually want to show that AB inverse whole square is equal to E, because this is the property of the given H. So we are going to start by this expression AB inverse whole square to check whether E comes out of it or not. Okay, so let's do it. Now, AB inverse whole square can be written as AB inverse into AB inverse. Remember one thing, when I'm writing square, this square is actually not the usual square that we mean for a particular number. Actually, this square means I'm taking the terms twice and I'm associating these two terms with one another by the binary operation that has been considered. This binary operation can be anything. So you have to be careful about that. Anyways, and for simplicity, we do not put the operation star over here. So we are actually writing x star x as x into x. Okay, it seems as if the operation is multiplication, but it is not. The operation can be any general operation. So you can do the entire calculation using star in between. Now you see, since the elements are associative in the group, so we can rearrange them in the following manner. And also, here I am going to apply the property. So far, I have not used this property of commutative group anywhere in this particular page. Since this property is given, somewhere it is required, and now it is required. What you can do, you can rearrange the terms. You can rearrange the terms in the following manner. So we can write it as A into AB inverse into B inverse. Okay, I can regroup the term because they are commutative. And now again, capital G is associative. So we can write it as A into A and B inverse into B inverse. Okay, now A into A, by usual notation, it is A square, and B inverse is B inverse square. But using star, you see that B is equal to B inverse. So in place of B inverse, I can put B. So we actually get A square, B square. Now, since A belonging to H and B belonging to H, so this implies A square equal to E and B square equal to E, we already know. So in place of A square, we can put E. In place of B square, we put E. And this is equal to E square, since we have already proved in equation number 2, and E square equal to E. This comes from 2. And therefore, what we find? We find that A comma B belonging to H. This implies AB inverse belonging to H as AB inverse belonging to G by closure property, and AB inverse whole square is equal to E. Okay, and therefore we can name it, you can number this as 3. Therefore, from 1, 2, and 3, capital H is a subgroup of the given group capital G, Q, E, D. Now, what will happen? Just try to look at this. What will happen if you do not consider this property? If I cancel this property, if I do not say that capital G is commutative group, then you can proceed as usual. No problem with that. But when you come to this point, let us put some marker over there. When we come to this point, then we cannot do this step, because this rearrangement can only be possible if capital G is commutative. Otherwise not. Then we'll be in a trouble, and we will not find any way to regroup the things and to get to this particular point. And therefore, this particular statement, capital G is commutative, is very important. It is not just an usual statement, it is a very significant statement for this particular problem. So therefore, we must consider this. Okay. Now, actually, see, lots of logic has been applied over here. And when I was a student and doing my honors course in mathematics, and when I learned about abstract algebra, I was very much afraid of this particular topic, because not afraid of because I was not understanding the things, but because we as mathematics honors student had to write all these statements as explicitly as possible. And that is just, I mean, a very hectic job, because the examiners over there, in my case, in our time, the examiner used to check each and every line, because we were mathematics honors student. They used to check each and every line to see whether I have actually done anything which is not logically correct. And if they are able to find any such statements in my answer, they used to put red marks over there. So we are very afraid about this particular subject. Okay, if you are afraid of this, then it is quite justified. I am actually agreeing with you. This subject is not the usual subject that often engineers like. Now, I'm going to give you a definition. This definition is also very important. It is also from the chapter of subgroup. In a group, capital G, define a special set like this. Okay, this capital Z is not the set of integers. This capital G is a notation. Okay, so ZG is defined in the following manner. We consider all the elements of G inside it such that Gx and X, G and X, they commute with each other for all G belonging to capital G. Okay, so what am I doing is that I am considering only those elements of capital G inside ZG, the elements which, when taken as mutual pair, they commute with each other. Some elements are there, some sets maybe, some groups may be obtained where some of the elements can commute with each other. Not all the elements commute. Such operations, such groups can be found. So if such a group is found, then we can consider all the elements which commute with that particular member of the group capital G. So if G is the member, X is actually commuting. This means what? If I write explicitly, suppose I'm taking an element G1 from capital G, and I'm saying that X G1 is equal to G1X for all X belonging to G. That means all the elements of X is commuting with the element G1. Then we have G2. Then we find that X G2 equal to G2X for all X belonging to G. So for all such G1 and G2, for all G1, G means for all such G1 and G2, this criteria is actually holding. If we can construct such elements, then such a set capital G ZG is called the center of the group. Center of the group. Right now, I cannot recall an example to show a practical example to show you center of the group. I cannot recall it right now, but during the process, if I can find, then I'm going to tell you for sure. Okay, but while doing the problem, if I can identify one such group, I'll talk about that. But right now I cannot recall any such group, so I'm putting a star over there. If I find an example, I'll definitely tell you. So such a set is called center of the group, and in this case, capital G is a commutative group. It is quite obvious because the elements of G are commuting with the elements, some other elements of G. So it should be a commutative group. Otherwise, this particular role will not be played properly. No. One thing I must this particular statement which I'm making must be rectified properly. If capital G is commutative, capital G is not always commutative, because as I've explained to you that for some elements it's happening. So G1 and G2, and if you can find similar G's over there, say Gn, for all such G's, the elements of G which we denote by X are commuting. Now, in this case, capital G is not commutative. Maybe commutative or may not be commutative. But if capital G is taken to be a commutative group, if I'm choosing the element from a commutative group, then there is no difference between the sets capital G and capital ZG. They become the same entity. So if you ask me, this is a very clever thing to say, I know, but if you ask me, sir, give me an example of a center of group, then I will say that, okay, so if you take into consideration this thing, then every commutative group is the center of the group. Okay, so that is the actually, I mean, this way I can also present it to you, but I'm sure that you will not be satisfied until you get something other than commutative groups, which from where we can find the center of the group. But once I can find this, I can recall that, I will definitely going to tell you about. But for the time being, let us console ourselves with the statement that all the commutative groups are actually the center of the groups. Now the problem, once again I'm going to give you another problem. The problem is, let capital G be a group. It is any group, not commutative group. It is capital G here is any group. Then prove that ZG, the center of the group, is a subgroup of capital G. Let us try to prove it. Okay, these results which I'm showing to you can be asked in online examinations as statements. So what type of statements they can give you regarding center of the group with respect to other properties that is related to center of the group? Say, for example, I can set a question in the following manner, that if capital G is when capital G is a commutative group, then which of the following statement is correct? If capital G is commutative, then G is subset of ZG, G is equal to ZG, G is not equal to ZG, and number 4, G intersection ZG is equal to 5. Now you have to choose the appropriate answer from this. So if you do not know this definition, then you will not be able to answer it correctly. Similar is the case with this one also. So these problems are very important. Okay. Now see, since capital G is a group, so it has the identity element, E in G. Okay, it has the identity element. We know that for all X belonging to G and for E belonging to G, XE equals to EX, which is equal to X, and therefore we can say that E belonging to ZG, E belonging to ZG, and so ZG is not equal to 5. This is your property 1. Let us now select, and also it is quite obvious. Also, it is obvious that ZG is a subset of capital G. Why? Because all the elements of ZG are chosen from the G itself. Now, one thing I must point over here. Suppose in the examination, the examiner is setting this question, okay, and he is asking you which of the following statement is correct. If G is commutative, which of the following is correct? Now, I'm pretty much sure that we all of us are going to tick on that. Okay, but if I don't know whether multiple option to be correct, these multiple correct options, this provision is there in the online examination or not. But if you carefully observe here in this particular problem, both the options 1 and 2 are actually correct. Why? If G is commutative, then capital G is obviously equal to ZG. And we know that ZG is in general the subset of capital G. ZG is in general the subset of capital G by definition always. So when capital G is commutative, what extra thing is happening? This is happening. And therefore, together, if we know that if together if we write G subset of ZG and ZG subset of G, then together they actually imply ZG is equal to G. So if the examiner is not cautious, then he can give you this type of questions where all at the same time you are not allowed to go for multiple options correct, if he is not cautious. But in competitive examination, if you are sitting for the competitive examination, then you have to be very careful about that, because the reverse is always true by definition. And for commutative group, this is true, this is holding for sure. Then what extra is holding? The option number 1 is extra holding. So both the options 1 and 2 are correct. Anyways, so by definition, ZG is a subset of capital G. Now we are going to take the going to show the last property. Let us choose two elements A, B from ZG. Okay, so we are choosing AB from ZG. By definition, BG is equal to GB, because there will be when A and B belonging to ZG, for all G belonging to capital G, we know that X belonging to ZG means X is an element of capital G, and for all G belonging to capital G, GX equal to XG. So BG will be GB for all G belonging to capital G, and AG equal to GA for all G belonging to capital G by definition of the center of the group. Now, if we start with that, BG equal to GB, this implies GB inverse is equal to B inverse G for all G belonging to capital G. Okay, why? Because I'm actually multiplying. Since you are actually multiplying by inverse from both sides. If I write, I'm going to multiply both the sides by B inverse, then from this that will come. Not one multiplication will give you the following, but you have to go for this type of multiplication twice from both the ends, and that will be true for all G belonging to capital G. And this will imply that AB inverse of G, AB inverse into G, that will be A into B inverse G, because it is associative as explained earlier. And since GB inverse equal to B inverse G, we can write it as AGB inverse, and they are again associative, so we can write it in the following manner, and then we can again write it as GAB inverse, because we know that GA equal to AG, and again they are associative, so we are going to write it GAB inverse. So what we are getting, just look at this, we are getting AB inverse G, and here I am getting G into AB inverse, okay, which is true for all G belonging to capital G, and therefore AB inverse belonging to ZG, AB inverse belonging to ZG. So H, or sorry, not H, ZG, this is equation number 3, and that I'm writing as equation number 2. ZG is a subgroup of capital G. GB equal to GB and BG equal to GB, and here you just do this calculation. In your copy you will find that this will come. Okay, you try to do it, and from these 3 points we can immediately set this result that center of the group is the subgroup of itself. Now you see that when capital G is commutative, and we know that ZG becomes equal to G, then it is, we know that G is subgroup of itself. It is also true. So this is actually being justified from the following result. That known result is also coming out of this. Okay. So just for practice, I'm going to give you one problem. You can do it by yourself because this session is going to end. So for homework, I'm going to this example. If G is a commutative group, if G is commutative group, then prove that H is equal to A square A belonging to G is a subgroup of G. Subgroup of G. This is one example that you can try by the similar approach by which we have I have done the two problems. And one another example that I'm going to give you is that, first of all, I'm going to give you a definition. This definition is, let H and K be two non-empty subsets of group capital G. The product HK is defined as all such elements of the form H into K, where the first element is from capital H and the second element is from capital K. Such a set is defined by HK. Okay. Now you are to prove that in this case, prove that HK is a subgroup of capital G. This is another homework that I'm giving you. So two homeworks I've given you. You just try later on. Once I, okay, you didn't note it down the homework. You just take the screenshot. If capital G is the commutative group, prove that this. And the second one is this one. Rest we are going to discuss in the second session.